Okay, so the next thing we are going to read is mass balance. Mass balance in open system flow. Okay, or open system or flow work. Okay, what is going to be the mass balance? Okay, so according to the law of conservation of mass, they have said that mass accumulated within the system, mass accumulated within the system is going to be equal to the net rate of mass transfer. Okay, that means whatever the mass is coming out per second or per unit time, whatever the mass is coming out per unit time and whatever the mass is going out uh, per unit time, okay, the net summation or the algebraic summation of this is going to be the mass accumulated within the system. Okay, that means what, suppose 5 kg per second of water is coming, okay, and through this only 3 kg of water per minute or per second is going to come out. Okay, then what is the amount of mass that has been accumulated within this system? It would be 5 minus 3. Okay, coming in is plus, going out is minus. So 5 kg per second minus 3 kg per second. Okay, 5 kg per second, 5 kg water is coming in and only 3 kg per second is going out. So what is the accumulation, mass accumulation rate? The mass accumulation rate would be 5 minus 3, that is 2 kg per second. Okay, that is going to be the mass accumulation. So according to law of conservation of mass, mass accumulated within the system is going to be equal to the net rate of mass transfer. Net means the algebraic sum of the mass transfer. Okay, so if we write it mathematically, it will be like this. Mass accumulation rate is going to be equal to m dot 1 minus m dot 2. Okay, this is going to be the mass accumulation. Now this flow system is considered to be a steady flow. Okay, our assumption for this type of flow work is going to be steady. Okay, so what do you mean by steady? Steady means what? If a steady flow is there, that means what? With respect to time, there is not going to be any change in the properties of a system. Okay, that means what? With respect to time, there is not going to be any change in the property. Now our system is this. Okay, whatever it is bordered by the blue dots, okay, this is our system. Okay, this is our system. Now here we have energy of the system, and energy is going to be a property. Same, mass is also going to be a property. Okay, mass is also going to be a property of the system. Okay, now for a second let us consider that this value is going to be positive. Okay, this value is going to be positive, that means what? Mass accumulation rate would be, that is m dot 1 is greater than m dot 2. Okay, that means positively there would be some mass accumulation, and if there is mass accumulation, that means what? The weight or the mass of the system is going to increase. The mass of the system is going to increase. Okay, now if the mass of the system is going to increase, that means the property of the system is changing. That means with respect to time, the property, that is the mass of the system is going to increase. Okay, so this cannot be steady flow. Okay, so as our assumption is steady flow, that means assumption is steady flow, that means the property, whichever the property is there of this system, this is not going to change. Okay, this is not going to change. That means we have to consider for steady flow, mass accumulation rate is 0. Only when mass accumulation rate is going to be 0, then only the mass of that system is going to be constant. That means with respect to time, it is not going to change, or the property, that is the mass of the system, is not going to change. Okay, then only we can consider this as a steady flow. So if this is going to be 0, we can easily write from this equation that m dot 1 is going to be m dot 2. Okay, and since they are same, there is no need of differentiation with respect to sections. We can simply say that m dot 1 equals to m dot 2 equals to m dot. Okay, this is going to be the inlet flow rate and outlet flow rate of the system. Okay, now from here you can see that m dot 1 is equal to m dot 2. Okay, m dot 1 is equal to m dot 2. So m dot 1 means what? We know that m dot 1 is equal to rho into a into velocity. Okay, rho into a into velocity is going to be the mass flow rate. Okay, so rho 1 a1 v1 and rho 2 a2 v2 is going to be constant. Okay, so this can be used as our continuity equation. Okay, this has been derived from directly this one. Okay, m dot 1 is going to be equal to m dot 2. Okay, Now if you ask me how this rho A B has come, rho A B means what? That means we have written m dot directly rho A B. Okay. So m dot means what? M dot is equals to mass per time. Okay. M dot is equals to mass per time. So mass, you can write it as rho density into volume, okay, per unit time. Okay, we know that density equals to mass by volume. So mass we can write from here, mass we can write as rho into volume. Okay, so we have written here rho into volume. Okay, now volume we can write it as cross sectional area into length. Okay, cross sectional area into length gives us the velocity, volume. Okay, now volume, now rho is there, A is there, and L per unit time is going to be velocity. Okay, L per unit time or length per unit time is going to be velocity. So from here we can write it as rho into A into V. Okay, in this way we have written m dot 1 is equals to rho into A into V. Okay, now from this whole derivation, this thing is going to be important and this thing is going to be important. Okay, for the last time I am saying that mass accumulation is going to be 0, or we are considering mass accumulation is 0 just because we are considering this a steady flow. Okay, this is going to be steady flow. Okay, so as this is steady flow, the properties of the system is not going to change. That means the mass accumulation must be 0 so that the mass of that system does not change. That's why we have taken mass accumulation is equal to 0. Okay, so the next thing we are going to discuss is open system work. Okay, so till now we have discussed all the closed system work. Every possibility of closed system work we have discussed, whether it may be any process, constant temperature, constant pressure, polytropic, adiabatic, every process we have discussed for closed system. Now we need to find out the open system work so that it will be easy for us to see the possibilities of open system under the banner of first law. Okay, so we have discussed whatever until now, whatever we have discussed was the possibility of closed system under the banner of first law. Okay, in first law, in conservation of first law, whatever the possibilities are there in closed system we have discussed. Now to analyze the open system, we need to see open system work. Now open system work may be of two types. Okay, external work and flow work. Now what is external work? External work is nothing but the work which can cross the boundary. Okay, work which can cross the boundary. Example, shaft work. Now if you remember, we have drawn a diagram. We had drawn a diagram in the previous videos like that. If this is the open system, mass of water is coming in from here, and mass of water is going out of the system from here. Okay, this was the boundary which we have discussed. Now in that thing there is a shaft. Okay, there is a shaft. Okay, now whether high temperature fluid comes in or low temperature fluid comes in, if that shaft is moving, okay, if that shaft is moving, then that means what, the work is going out of the system. Okay, which is being turned due to the flow of mass, flow of fluid. Okay, flow of the fluid which is coming out with the temperature, and it is going out with different temperature. So all these potentials will try to turn this shaft. Okay, now with the turn of this shaft, some of the work is going out of the system, so that we can utilize this work out of the system. Okay, out of the system we can utilize this shaft work. Okay, that means what, the shaft work is crossing the boundary. Now if it is crossing the boundary, then this thing is known as external work. Okay, and another one is flow work. In flow work, what happens? The work which is responsible for the flow of fluid, okay, it is known as flow work. That means what, if any particle or element is responsible to go into the system, okay, if any particle or element goes into the system, and for that the flow is responsible, whether it may be going into the system or coming out of the system, if it is due to the flow of the fluid, then we call it as flow work. Okay, that means if there is a system and some of the fluid is going into the system and the flow of the fluid is responsible for that element to enter into the system. And if some of the element is coming out of the system, okay, and the flow of the fluid is responsible for that element to come out of the system, then this is known as a flow work. Okay, it is also analogous to displacement work. Okay, now and again we have written that it is because of the normal fluid force. Whatever the element which is going into the system or coming out of the system, it is due to the normal fluid flow. So this total phenomenon is known as flow work. Okay. Okay, so as we have discussed that the flow work is the work related to transferring an element or some amount of fluid entering into the system. Okay, okay, to make some element or an amount of or a mass of fluid to enter into the system or going out of the system is known as flow work. So for an open system, now we are going to derive the flow work which is going to be there to displace, or that means to make this small amount of fluid to move into the system. Okay, so for this let us take a small element of fluid. Okay, small element of fluid which is having mass dm and volume of dv. Okay, that means the small amount of mass which we need to move into the system, and for that what would be the work done in an open system, we are going to find out that. Okay, so this is the element. So to make this total element go completely into the system, what should be the distance covered by the this element? What should be the distance covered by this element? This must be exactly equal to dx. Okay, suppose the length of this element is dx. Okay, to make this element completely go into the system, what should be the distance traveled by this element? That should be dx. Okay, and the fluid flow force letters, that is F. Okay, for F force we need to with the help of F force we need to make this element go into the system by a distance of dx. So work done, so flow work must be what? Force into displacement, that means F into dx. Okay, now F we can write it as pressure into area. Okay, whatever the water pressure it is giving, we are taking this as water. Okay, suppose water is coming in and water is going out. Okay, so for this what happens, to see that whatever the fluid pressure that fluid is given into the cross sectional area of that element will give us the force. Okay, whatever the force is there, it will be the product of pressure into cross sectional area. Okay, so pressure into area into dx. Okay, again this part, area into dx gives us what? Area into dx gives us the volume. Okay, that small volume, whatever that small volume which the element will cover to go into the system. Okay, that is area into dx. That will be the total, or you can also say that this area into dx is the volume of that element which will go into the system. Okay, dv, and this is also equal to the area equal to the volume which this element will travel. Okay, it is similar to swept volume. Okay, that means whatever the volume this element is going to cover to go into the system, this is known as dv, or you can directly say that the element having the volume dv. So area into a into dx will give us dv. Okay, now again we know that specific volume is equals to dv by for this small element, what would be the specific volume? The specific volume is the ratio of volume by mass. Okay, so for this small element, what is the volume? It is dv, and it is divided by dm, which is the mass of that element. So the ratio of these two will give us the specific volume. Okay, now specific volume, from this we can write it as like this one. Okay, so dv is equals to specific volume into dm. Okay, specific dv will be equal to specific volume into dm. Okay, that means what? The volume of any element or anything is the product of mass of that thing into specific volume of that particular thing. Okay, that means dv equals to v into dm. Now we can replace this one. We can replace this one by this equation. Okay, where nothing is done, only dv is replaced by v into dm. Okay, only the term dv is replaced by v into dm. Now if we divide dm, dw flow, that means the flow work with the dm, that means if we divide w flow by dm, we will get p into specific volume. Okay, so this is for a small element, this is for the small element. Okay, now complete, if we consider the complete system, what could be the small work, or if we need to find out the small flow work in general terms, we can say that flow work, that means dw flow is for small element. Okay, now to generalize this, what you can say, that flow work divided by mass. Okay, flow work divided by mass will give us the p into specific volume. Okay, now in cross multiplication, if we see that mass will go this side. Okay, mass will go this side, that means specific volume into mass will give us the complete volume. Okay, specific volume into mass will give us the complete volume. So we can write that flow work equals to p into complete volume, and complete volume is what? It is nothing but v into mass, which we have written here. Complete volume of that element is equals to the specific volume into the into mass of that specific element. Okay, so to generalize this, we can say that v into mass will give us the v. Okay, now another thing you need to remember here, at the entry the flow work is p1 v1, but that would be negative. That means what? p1 v1 is the work done to move this element into the system, or to make an element go into the system. This is the work, but this would be negative. Why this would be negative? Because by giving this element into the system, we are working on the system, and work done on the system is always negative, which you have seen in the sign convention of work. Okay, so by moving an element into the system, we are making sure that it is work done on the system, and work done on the system is always negative. Okay, and while at the exit, p2 v2 would be the flow work. That means it is responsible, this work is responsible to move an element out of the system. Okay, to move an element out of the system, p2 v2 is responsible. Okay, so p2 v2 will always be positive, because what? It is taking an element out of the system, that is work done by the system. Okay, and work done by the system is always positive. So this is an important point we need to remember, and this is the flow work. In other words, we will also discuss in the next parts. Okay, okay, so the next thing would be energy balance. Okay, the next thing is energy balance. It is similar to mass balance only, but one simple word has been missed out in mass balance, which was that the mass, we have considered the accumulation of mass is going to be zero, because we are considering all these systems as steady process. Okay, all these systems as steady flow process. Okay, now in steady flow, what happens? These properties does not change with respect to time. Okay, so mass is also a property, energy is also a property. Okay, so in the previous case where we have discussed the mass balance, the mass accumulation is going to be zero, because it was a steady flow. Okay, and the mass, which is the property of that system, that is in control volume, mass is the property. Okay, so mass is not going to change with respect to time, that is steady flow. That's why the accumulation of mass we have taken as zero. So m1 was equals to m2, that means the net rate of mass transfer was equal to zero. Similarly in energy balance also, energy balance, what happens? At the entry the fluid is also having some energy, at the exit it is also having some energy. Okay, now according to the energy balance, that is based on the law of conservation of energy, what does the statement say? The statement says that the energy, the rate of accumulation of energy into the system is going to be equal to the net rate of energy transfer into the system. Okay, net rate of energy transfer into the system is equal to the total energy accumulation into the system. Similarly, like mass conservation. Okay, conservation of mass. Okay, it is similar. Okay, now what happens? Since this is steady flow, the energy accumulation is going to be zero. Okay, suppose this is having energy E1 and this is having energy E2. So as this is steady flow, the energy accumulation is going to be zero. And what they have said? They have said that energy accumulation must be equal to the net rate of heat transfer. net rate of energy transfer. Okay, so rate of energy transfer is going to be, okay, that means net rate of energy transfer is going to be this minus this one. Okay, this must be equal to 0 because the energy, that is the property of the system, must not change with time. Okay, this must be equal to 0. For this reason E1 is equals to E2. Okay, now this is the finding, or this is the final expression which we can say for the energy balance, or law of conservation of energy. Okay, now what happens, what you have said that in the previous while discussing the first law of thermodynamics, we have said that the energy is consisting of several terms. Okay, this is the one internal energy of the system, or in this case the energy of the fluid. Okay, in open system there is this E. Okay, this E2 or E1, whatever it may be, this energy consists of several terms. Okay, it consists of kinetic energy, it consists of potential energy, it consists of the energy of that fluid. Okay, and the extra energy is whatever the heat we are giving, because our motive is giving heat and taking out energy. Okay, so whatever the heat we are giving, that means heat entering into the system is also going to be considered as energy of entrance. Okay, and the work is also an energy, and whatever the work we are taking out will be considered as the energy at the exit. Okay, so after writing this, E1 consisting of, this is half into mv square. Okay, half mv square, it is rate of change of energy, so it will be half into m dot into v1 square. Okay, kinetic energy per unit time. This one is potential energy, m into g into z1. Z1 means what? This height. Okay, or some datum is there, so the height of the datum will be z1 and this would be z2. Okay, that means the height of the entry from the datum is going to be the height of the fluid at entrance, and this z2 is the height of the entrance from the datum line, is going to be the height of the height. That means this height will give us the potential energy of the fluid coming out from the through the exit. Okay, so these are several terms which consists of the energy. Okay, this energy. Okay, so this is kinetic energy, this is potential energy, this is internal energy, and this is the heat we are going to give. These all consists of E1. Okay, these all together sum up to become E1. Okay, in E2 what happens? Similarly kinetic energy at exit, potential energy at exit, internal energy at exit, and whatever the work we are going to take out from the system is going to be W. Okay, now this is the W which we are talking about. This W is going to be of several types: flow work and external work. Okay, external work is whatever the work that is done by the fluid of the system and which is crossing the boundary. Okay, and in flow work there are two things. Okay, in flow work there are two things. Okay, at the entry, which we have discussed in last board. What is there? There is minus P1 V1, that is flow at flow work at entrance, and P2 V2, that is flow work at exit. Okay, so considering this, that means this W consists of flow work and external work, and flow work is again these two. Okay, so we have written the same thing. Okay, that means this is kinetic energy, this is potential energy, this is internal energy at exit. All of these are at exit. These two consists of flow work, P2 V2 minus P1 V1. Okay, this is minus P1 V1, this is P2 V2. Okay, so these two consists of flow work. Okay, and this WCB is whatever the work is done by the control volume. Okay, that is the external work. This consists of this one. Okay, so now what happens? According to the energy balance, we have seen that E1 is equals to E2. Okay, E1 is equals to E2. Now in the next board, what we will do? We will add up these two. Okay, that means this E1 must be equal to E2. So in the next board, we will derive an expression for work done in, or the first law equation for an open system. We have discussed the first law equation for closed system. Now we will derive the equation for this one. Okay, for open system the first law equation we will derive. The next board we will equate E1 and E2 and derive an expression. Okay. Okay, so now as we have said that we are going to equate U1 and E2, so similarly we have written here. Okay, this part is total U1, this part is total U1, and at the right side there is totally U2. Okay, now we need to derive the expression. I could have written down all these expression and later I could have explained, but this is a long equation. Okay, this is a long equation with lot of terms. Okay, so if I write down all the equations and then explain, it will be a difficulty for you to understand, so that's why I am writing this down. Okay, now what happens, we can write this as m dot into v1 square plus m dot into g into z1. This thing is going to be same. Now what happens, we are writing u1. U1 is the complete internal energy of the system. Okay, that is the complete internal energy of the system. Now what is specific internal energy? Specific internal energy is total internal energy divided by mass. Okay, so this thing we can write it as m dot into u1. Okay, because small u1, that is specific internal energy, is going to be u1 by m. So if we cross multiply, this will be u1 equals to m into u1. So this u1 we are breaking down as m dot into u1. Okay, plus again we are taking this one. Okay, p1 v1 is will also come here because this is the energy at entrance and this is at right side, so we'll take it to the entrance side. These are all the energy at entrance, so we will take p1 v1 in this side. Again p1 and v1 we can also write it as m dot into small v1 plus q. Okay, now for the right side everything is going to be same, half into m dot into v2 square plus m dot into g into z2 plus again this u2 we are also going to break as m dot into u2 plus again this one p2 into m dot into small v2 plus w. Okay, so like this we have written the second part. Now if you see this part and this part, from these two parts, okay, m dot is going to be common. Okay, so if you take m dot common from these two parts, we will get u1 plus p1 v1 plus half into m dot into v1 square plus m dot into g into z1. Okay, we are writing kinetic energy, potential energy. Okay, and this from these two terms we have written down here, taking down the m common. Okay, plus q. Similarly from this side also, this term and this term are having m dot as common, so this will be m dot into u2 plus p2 into v2 plus, okay, plus kinetic energy half into m dot into v2 square plus m dot into g into z2 plus w. Okay, now this u1 plus v1, u1 plus, we have already seen that u1 plus u1 u plus pv. Okay, u plus pv term is always the enthalpy. Okay, now here u1 is also specific internal energy, v1 is also specific volume, so whatever the enthalpy we will get, this will be specific enthalpy. Okay, while explaining enthalpy we have said that enthalpy is nothing but it is the term u1 plus p1 v1. Okay, or u plus pv term is known as enthalpy. So here u1 is also specific and v1 is also specific, that is specific internal energy and specific volume. Okay, so this u1 plus p1 v1 will give us the specific enthalpy. Okay, again another thing you can see that from all these three things, all these three parts, m dot is again common, so we are taking m dot. Okay, m dot common, and this one u1 plus p1 v1 will give us the specific enthalpy at entrance. Okay, u1 plus p1 v1 will give us specific enthalpy. Now from here m dot is common, that means remaining is what, volume square by 2. Okay, and from here m dot is common, so g into z1. Okay, plus q is equals to, again from this side also, from these three parts m dot is again common, so we can write this as m dot into u2 plus p2 v2 will give us specific enthalpy at exit plus m into v1 v2 square, so this will give us as v2 square by 2 plus g into z2. Okay, again m dot is common, so this will be g into z2. Okay, plus w. Okay, now while solving the questions you will see that in each and every question the value of enthalpy will be given as in kilojoule per kg. Okay, while this will be given as v1 will be given as meter per second, this will be in SI unit for to get. So these two energies, again this height will be given in meter or centimeter, you need to convert it in meter. Okay, so while solving this you will see that this term is in kilojoule, okay, and these two terms will be in joule. Okay, so this is the expression, no doubt that this is the expression for open system, okay, energy analysis. But while solving the questions you will find some difficulties while putting the values whether in kilojoule or joule. Okay, so this term will be already given as kilojoule, always this will be given as kilojoule. Okay, so while converting, so next thing you need to know that if this is given in kilojoule, we have to make sure that these terms is also in kilojoule. Okay, these terms are also in kilojoule. Okay, so what we will do, we will see another equation. We will see another equation where this total thing will be found out as in terms of kilojoule. Okay, so what can we do? When putting the values in solving questions, we have already said H1 will be already given in kilojoule. Okay, now to make this one as kilojoule, what we will do? This is in joule. Okay, so this is in joule. To make this in kilojoule, you need to divide it by 1000. Okay, so we will divide it by 1000. So that is V1 square by 2000. Again G into Z1. Again to turn this into a kilojoule, what we can see? We will see that this is divided by 1000. Again heat will be given as and this will not be tough. Converting kinetic energy and potential energy by multiplying G into height and velocity square divided by 1000, these are difficult. So we are only dividing these two terms by 1000. Okay, Q you can easily convert it into kilojoule by dividing by 1000. Okay, so we are taking Q as it is. Okay, similarly in the right side also m dot into H2 plus V2 square by 2000 plus G into Z2 by 1000 plus W. Okay, now this is the term where you can find all the energy into Q2. Now what is the unit left side and what is the unit right side? That means these two units are going to be same only, but what is it? This is m dot. M dot means what? Kg per second. Okay, and these terms are in kilojoule per kg. Okay, these terms are in kilojoule per kg because this is specific enthalpy. Specific enthalpy is always in kilojoule per kg. Okay, so this specific and this thing will give us the since this is kilojoule per kg and these are in addition, so these terms will also be in kilojoule per kg. Okay, so if so we can say that for all this the unit of all these three terms is going to be kilojoule per kg and m dot is kg per second. So these are in multiplication relationship. So what we can see that kg gets cancelled. That means what? That means all the terms which is there in the left side and all the terms which is there in right side, all these terms are having the relation, having the unit of kilojoule per second. Okay, all these terms are having the unit of kilojoule per second. Okay, kilojoule, these terms are going to have the equation as kilojoule per second. Now if we divide this thing by mass flow rate, what will happen? If we divide all this thing by mass flow rate, which will what will happen? This will give us the, just see, if we divide all this term by mass flow rate, what will get? Mass flow rate and mass flow rate will be cancelled. So here will be H1 plus V1 square by 2000 plus G into Z1 by 1000 plus Q. Q if you divide by mass flow rate, what will happen? This will be small q, okay, small q, that is per unit kg, okay, or per unit mass, heat per unit mass. This will be written as small q. Similarly in right side also, if we divide all the terms by m dot, what will happen? H2 plus V2 square divided by 2000 plus G into Z2 by 1000 plus again this W will be small w, okay. Now what you can say, for this equation all the terms was having the unit of kilojoule per kg, while we have divided these terms by m dot, okay, while all the terms were in kilojoule per kg. Now we have divided it by mass flow rate, okay, mass flow rate, that means what? M dot, okay. All the terms, so all the terms before in this equation, all the terms were in kilojoule per second, okay. Now we have divided all this thing by mass flow rate, that means second per kg. Now second gets cancelled, that means while dividing by mass flow rate, what will happen? Whatever the equation which you have got here, this thing will have the equation in, this thing will give us the equation in kilojoule per kg, and this thing will give us the equation in kilojoule per second, okay. So these are the two equations which is very important for you to remember while solving the questions from open system, that is like nozzle, turbine, etc. These things are going to be very important, okay. So we need to remember that this equation will be having all the terms with unit kilojoule per second, and this term will have all the units in kilojoule per kg, okay. So this is the equation of open system, okay. Now we will see some examples of steady flow devices, okay, open system. That means we will see some of the examples of open system. Likewise we have seen the closed system examples, okay, rigid tank, piston cylinder arrangement. Likewise we will see some examples of open system devices, okay. Now the first thing is nozzle. Now what is nozzle? Nozzle is a device which is used to increase the velocity of a fluid flowing through a pipe or a duct, whatever it may be. Nozzle is used to increase the velocity, okay, with the expense of its pressure energy, okay. That means nozzle is a device which converts its pressure energy to velocity, okay. That means kinetic energy. So when the kinetic energy is increasing, automatically the velocity will increase, because kinetic energy is half mv square. Since mass is not changing, so velocity will also increase, okay. So this is the diagram of a nozzle, okay. So in this way water will be coming, and in this way it will go out. So when this will pass through this one, okay, it will pass through this one, the area is contracting, okay. When area is contracting, what will happen? The area will decreasing, so velocity will increase, okay. So according to Bernoulli's principle, this Bernoulli's principle, what is Bernoulli's equation? What they say that P1 by rho g plus V1 square by 2g plus Z1 is going to be constant, okay. Now to increase the velocity, Z1 is same, okay, Z1 is not increasing. So to increase the velocity, pressure energy is going to come down, okay. That means with the expense of its pressure energy, this nozzle is going to increase the velocity, okay. Now what happens? We need to analyze this, okay, nozzle in terms with the equation which we have found out in the last board, okay. So this is an open system, obviously, because mass is coming in and mass is going out. So and this is one control volume, okay. Now to analyze this, we are writing the open system first law equation, okay. The steady flow considerations are steady flow, open system, mass flow equation, okay. Open system first law equation, okay. Now in this thing, what is happening? This Z1 and Z2 are going to be same. That means that from the datum, the height of the entrance and exit is going to be same. That means the potential energy is going to cancel out, okay. That means there is no difference of potential energy from here 1 to 2, okay. Now second thing is that it is completely insulated. Completely insulated, that means what? heat transfer is also going to be 0. And since it is a nozzle only, it is a duct type shape only, since there is no shaft, that means shaft work is also going to be 0. Okay, so that means from here we can write that H1 is equals H1 plus V1 square by 2000 is equals to H2 into H2 plus V2 square by 2000. Now 1 and 2, okay, 1 and 2, that means what, here velocity is too much low, okay, and here velocity is constantly increasing. Now if we consider that C1 or velocity 1 is very less than velocity 2, because here velocity is completely increasing. Okay, if it is increasing and becomes a value which is very greater than this one, okay, that means V1 is very less than V2, what we can write, V1 is going to be 0. Okay, so from here what you can write, we can, sorry, this will be 2000, so we can write V2 square will be equal to H1 minus H2 into 2000. Okay, so V2 will be equal to root over of 2000 into H1 minus H2. Okay, while solving the question, if V velocity at 1 is not given, you can easily find out this one. Okay, you can easily find out V2 if the V1 is not given. Okay, that means if V1 is not given, they are meaning that V1 is very less than this one. Okay, V2. So we can easily find out V2, and this is going to be the equation for a nozzle where work done by shaft is 0, heat transfer is also 0, but the remaining thing, considering the remaining thing, we can easily find out V2. But if V1 is given, you never come to this one. If V1 is given, you can directly calculate it from this one. Okay, but if V1 is not given, you can calculate V2 with the help of this equation. Okay. Okay, now the second example is going to be turbine and third example is going to be compressor. Now we are taking this together because these are two completely opposite with same principle but completely opposite. Okay, so turbine is what? Turbine is it is expanding gases to give us some work. Okay, turbine, if you highly compressed gas is coming through a turbine, it will give us work and it will expand the gas. Okay, whether in compressor, what happens, it is a work consuming device. It will compress the air. Okay, it will compress the expanded air and it will consume the work, whereas the turbine is a work producing device. Okay, this is work producing and this is work consuming device. Now first of all, let us consider the turbine for analyzing with the first law for open system. Okay, now what happens, we have written down the equation for first law of open system. Now here also from datum, the entrance and exit heights are same, so potential energy is going to get cancelled out. Okay, now velocity does not change that much, velocity also does not change that much, whereas we can say that we are ignoring the kinetic energy change. Okay, so velocity is also going to get cancelled. Okay, because this doesn't change that much, the change is negligible. Okay, and this is completely insulated, so Q is also going to be 0. Okay, so what you can see, this Wt is going to be H1, and if we take H2 this side, this will be H2. Okay, that is Wt is going to give us the H1 minus H2. Okay, now this is for specific enthalpy only. Now if you need to find the total work done by the compressor, you need to multiply m dot into H1 minus H2. This is for unit mass only. Okay, this H1 minus H2 will give us the work done per unit mass of the fluid whichever is coming through the turbine. Okay, and this will give us the total work done. Okay, total work done by the turbine. This will give us per unit mass. Okay, this will give the total. Similarly in compressor, what happens, again similarly the change in velocity is not that much, so kinetic energy change is negligible, it is insulated, so Q will not be there, Z1 and Z2 is going to be same, so this is W compressor. Okay, now W compressor is work consuming, so in this place it will be negative. Okay, Now what you can see, we can see that W minus of WC is H1 minus H2. Okay, that means WC will be equal to H2 minus H1. That means what happens in turbine, what happens, the initial enthalpy is greater than the later enthalpy. Okay, when the gas expands, the heat content of that air comes down. That means the H2 will always be lesser. Okay, whereas H1 will always be greater. Whether what happens in compressor is you give the air with one enthalpy, it will compress it, so the heat content will increase, so enthalpy will also increase. That means the enthalpy at the final stage, okay, enthalpy at the final stage is always going to be greater. Okay, because after compressing, the heat content increases, so enthalpy increases. Okay, so WC C is H2 minus H1, whereas in a turbine it is H1 minus H2. Okay, so the total work needed for the air to compress is going to be mass flow rate into H2 minus H1. Okay, so this is the analysis of turbine and compressor in terms of fast flow open system. Okay. Okay, the next thing is throttling device. Throttling device, what is there? There is nothing. This is a throttle in a pipe which we have taken. Throttling device, for analysis of this we have written down the equation here. Okay, now similarly the height of this is going to be same. Okay, that means Z2 and Z1 are going to be same, so potential energy change is also going to be 0. Velocity is also not going to change, since the cross section is also not changing. Velocity, that means the change in kinetic energy is also going to be 0, and it is insulated since no heat is going to get transferred. So this thing is completely insulated, so heat transfer is also going to be 0. And since there is no shaft, so work output is also going to be 0. Okay, work output or work input, it is going to be 0. So what happens in throttling device, H1 is equals to H2. Okay, so in any of the process which is taking place through a throttle, it is always considered as isenthalpic process, because enthalpy does not change in throttling device. Okay, in a throttle device, if there is a throttle, and in some of the topics of the refrigeration you will find it easier, okay, if you know this thing right now, that in a throttling device enthalpy is not going to change, enthalpy is going to be constant in a throttling device. So this ends the examples of the steady flow in open system. Okay.